Thank you so much for coming out this evening, and thanks so much for having me here. This is a terrific honor, and actually I just snapped a picture of the poster on the way in, and I was just thinking about what young me would have thought about being here. When I was in graduate school, Kenneth was running around, and he taught me many things. He was, of course, did lots of different things and was good at them. He would also fall asleep during seminars and then wake up and have a really good question. And that taught me that it was okay to fall asleep in seminars. No, just kidding. I have a bit of ADHD, so I think that showed that you could think different ways and your brain might work differently, and that would be okay. Joe Stiglitz was advising one of my colleagues at Stanford, and there's so many, just like there's so many Ken stories, there's so many Joe stories. I think the one that stuck with me for today is that he would sometimes proofread Joe's papers, and the joke was that they would have sign errors in them, but there was always an even number of sign errors because he knew what the right answer had to be in the end. And so also being perfect with algebra didn't prevent you from doing, or being imperfect wouldn't prevent you from succeeding. So today I'm going to talk about a series of papers that are trying to study worker transitions. And some of the work is using machine learning, and some of the work is using digital technology to help people, and then evaluating it using both standard methods, like from randomized experiments, but also although I won't have as much time to talk about it today, even those papers use machine learning as well to look at things like the benefits of personalization. So I'm going to start out with a project that is kind of motivation, if you like, for the whole line of work. And that's a paper about the impacts of layoffs and the heterogeneity in that impact. And so there have been many, many papers in labor economics that study what happens when workers lose their jobs. Layoffs are useful to study because when somebody leaves the job, of course, it's hard to know why, and those are different than the workers that stay. But at least when there's a layoff, it's about a group of workers, but not their individual characteristics. But despite the very large literature looking at those, most of the time when economists try to study who's hurt and who's not, we do very simple types of cuts, like men and women, or college versus non-college, and so on. And there's a good reason that we do those simple cuts, because we're worried about bad data mining or p-hacking. We're worried if we keep fishing, we'll eventually find something and it won't be reproducible. And so one of the things that I'm going to use today are machine learning techniques that I've built that kind of get around that problem through a combination of sample splitting and kind of using an algorithm to find the groups that are most and least hurt. So in terms of the results, so what we do is well, let me describe a little more about the setup. So the setup is I mentioned that on this slide. We matched 180,000 laid-off workers across 22,000 plant closures in Sweden. And so we matched those workers to other workers who are similar, both in terms of the worker histories and the establishments that they're a part of and the locations that they're in. So we do a rich matching exercise to find similar workers. And then we take the layoff is sort of the treatment, and we look at the treatment effect. So we use machine learning, in particular this causal forests method that I've developed, and we have if you haven't checked it out, we have a very popular R package that implements this. And you can think of how we make sure the results are valid is we use part of the data to put people into groups according to their treatment effect heterogeneity, and then we use another part of the data to evaluate the effects. So you don't have to worry about whether my model is right or not. I'm going to sort of show you what the model produces on kind of fresh data. Okay? So the outcome we train for is 1 year after earnings. So the model, when it's creating these groups, sees the outcomes 1 year after for some workers, but not the workers whose outcomes I'm showing you on the screen. And it doesn't at all see for any workers outcomes 2, 3, 4, 5, 6, 7, 8, 9, 10 years after the layoff. Okay? So in this picture, there's a lot of information. What we've done first is we use the machine learning model to put people into deciles, 10%, 20%, 30%, et cetera, in terms of the magnitude of the treatment effect of the layoff. And so what I've plotted here is the bottom decile, the people who are the most harmed, the top decile, the people who are the least harmed, and the decile containing the median. And what you see in the years below zero is the treatment effects of the people before they were laid off. And you see that we're estimating treatment effects of 0, and that's showing that we did a good job with our matching. After the layoffs, we see effects for the most harmed group. That's the biggest dip. It's about a 45% loss in earnings the year after they're laid off. And again, the model's only trained for that first year that's highlighted in red. But we see that group is still about 13%, 12% less in earnings than the control group. The treatment effect is minus 0.12, 10 years after the layoff. So for that group, the layoff was a permanent event. And so what this says is that based on characteristics of people before they were laid off, we can very accurately predict on held out data people who are going to still be badly off much later. While there's another group that is still harmed, but the effects are much smaller in magnitude and they go away by about year 8. Then to try to kind of dive into this a little bit more, the top left panel is the same graph that I just showed you. Then on the top right, I'm showing for the top decile, I'm breaking out the treated and control group. And the difference between those lines is the treatment effect that's plotted on the top left. And so what that shows for the top decile of people is that the people who were resilient were kind of on an upward trajectory, and the layoff takes them a little bit off of that upward trajectory, but these people were doing well, and the layoff doesn't hurt them. If you jump down to panel D, the bottom decile of people, we see that the control group, the solid line, was on a bad trajectory without the layoff. So the people who weren't laid off, still over time, their earnings were going down, like they might have been laid off later or something else. So they were on a downward trajectory. They were vulnerable, but the people who were laid off did much worse. Okay? So this can, although this doesn't tell you exactly what policies work, it can help shine a light on policies that you might want to think about, and particularly what programs governments should consider to do this. And in the paper, we actually also incorporate the social safety net, which has been getting not as helpful over time, and so we see that the impacts are greater in more recent years. So then this gets into targeting. One of the things that you can do with machine learning methods is to think about how to target. And it can also be, hypothetical targeting exercises can also be used to kind of exposit what is the value of different types of data for prioritizing people or for identifying the people who are harmed. And so in these 4 panels, we try 4 different types of targeting exercises to try to see what variables, if you targeted on them, would identify the people who are most harmed. So the blue lines at the top are like random targeting. So if I took a random person from the data set, they're about minus 0.22, those are the blue lines, harm. So the average person is harmed by about that much. If we take the red lines, say if we read off the points, and the red line is the same in all 4 panels, that's using GRF targeting. And so corresponding to point 1, that's saying what happens if we picked the 10% of people who were most harmed, then we get about 46% impact. And as you see, the red line is sloping up. As we include more and more people in our targeting group, the effect moves closer and closer to the average effect. Okay? So then we look at what happens if we target in the panel A based on schooling or based on age. And we see that targeting based on schooling or age is not as effective at identifying harmed people as targeting using the random forest. It's effective, but it doesn't capture all of the richness in who's harmed. Nonetheless, if you just targeted based on age, and it turns out to be like older people who are more harmed, that would already help you identify who's harmed. And of course, policies for people who are close to retirement might look very different than policies for people who are not. Then in panel B, we look at market variables, and we see that targeting based on manufacturing misses a lot. It's really like old people in manufacturing and combined with other things that are most harmed. Just there are people in manufacturing who are perfectly fine. So the green line is the manufacturing line. Population density of the market doesn't actually do anything. Then in panel C, we start looking at combinations. We look at manufacturing and schooling. And if you put manufacturing and your education level, that starts getting much closer to what the random forest identifies. So just those two variables, or manufacturing and age, does a little bit better than manufacturing and schooling. So it's really the older or low-educated manufacturing workers that the machine learning model finds. But so then once you know that, maybe you can throw the machine learning model out. But the machine learning model helps you understand that if I just look at those two interactions, I'm getting pretty close to what a more complicated policy would tell me. All right, so that's in Sweden, and that's manufacturing. I'm going to now show you two interventions and randomized experiments I ran to evaluate the interventions that are designed to try to help workers navigate transitions. There's a little disconnect here. This is, sadly, my work doesn't all completely follow a linear trajectory in that these applications will not be aimed at manufacturing workers because it's harder to help those people, frankly, and it's harder to, the interventions that I'm gonna show are digital interventions. The advantage of the digital interventions is that they are going to scale really nicely, and they're also easier to evaluate, but they're probably not helping Swedish manufacturing workers. All right, so let me give a little bit of a framework for how we're thinking about the problem of digital interventions to help people make transitions. So the starting point is that skills, I could give people skills, I could give them training, I could give them digital training, I could give them non-standard credentials, and that's gonna be cheaper than sending people to college. But that's only going to be helpful if that can be credibly communicated to the employer. And of course, it also depends on what does the employer believe about that credential. So we're from the agenda perspective, we can think about improving approaches that help you demonstrate your skill. That's going to be one part of this pipeline. If you can't demonstrate your skill, there's no point in having it. And then we can also think about, okay, if we can show that it works, if you have a digital skill or a non-standard credential, if we can show that a non-standard credential does move the needle with employers, then we can invest in building those skills and getting more people to get the credentials. But one of the reasons I started thinking about breaking this down is during the pandemic, some countries and governments were asking, like, what can we do? Maybe we should try to spend a lot of money getting people education during this time. And the problem is I could say, okay, let's spend a couple $1 million and try to convince a bunch of people to take courses, but that's expensive, especially if I'm trying to do like some kind of randomized experiment. I've got to sort of convince people that wouldn't have otherwise taken the courses to take them, that it's costly, it takes their time. And I'm not even sure whether once they get a credential, that credential will help them. So I wanted to really think hard about the process through which employers receive that information before going out to investigate, the harder problem of getting people skills. I want to mention a couple of things that I don't solve in either of these two papers, but that are very important, and they're really like fundamental problems to this type of work. And that's partial versus general equilibrium. So I'm going to show you one program that was very small. So if I want to think about evaluating that program, it didn't have any general equilibrium effects. But if I tried to scale it to a whole country, then did I do that? Or then it might have general equilibrium effects. And so again, credentials are valuable if employers learn their meaning. So when you first launch a credential, it might look like it has no effect because there's a chicken and egg problem. I've never heard of the credential. I don't really care about evaluating somebody with it. That's why a degree from someplace like Columbia has value, because people already have decided it has meaning and they don't have to go and look it up. It's less valuable if it's more common. So if I give 100 people in a country versus 10,000 people the same credential, there's like downward sloping demand for that credential. So that's a negative effect on the demand for the credential. And then actually in the future, everything about this is going to change because AI might, change the way people signal and change the way employers evaluate. And so everything about the way a credential is received could change as it shifts from humans to AIs doing the evaluation. Definitely not solving that today. Okay, so with that framing, the first paper we're going to look at is a digital program that helps women build portfolios demonstrating skills relevant to IT jobs. And so manufacturing declining in a lot of developed countries, IT growing, we want to help people do this. And so that's going to be hitting the part of this chain where they both are building skill and demonstrating the skill. So we're going to help them build a portfolio that demonstrates their work. It's kind of like a job market paper for those PhD students and faculty here. That's a project that shows that you have the skills. So this is a project that we worked with a very small organization in Poland. It's kind of a for-profit small organization that works on women in IT, and then they had this small not-for-profit mentoring program that they were running when we met them. And it was like 2 people or 3 people running this mentoring program. And it's sort of similar to some of the things the American Economics Association does and other things where it's trying to match up a mentor with a mentee and then try to help them gain skills and network as well. So we then said, well, that's great, but what's the problem? They said, well, the problem is there's not that many mentors. Like, we're trying to get women into the IT industry in Poland, which is growing, but there's not a lot of women there, and so they're going to have a hard time. It's a hard time to scale the program. So they were doing about like 200 or 300 women at a time, like every 6 to 8 months. So this program, the mentoring program, is what they were doing, and so we proposed to them to create a new program. So we actually developed the program entirely because they don't really have any people to do it, so we developed it in collaboration with them. And they managed, but they used their existing web presence and kind of Facebook page and so on, and LinkedIn to kind of recruit people into the program, and then they managed the administration of the program. And I'll show you in a minute, this was successful, and they're still running the program. When the war with Ukraine and Russia broke out, they actually had one that brought in Ukrainian women, so who had come to Poland. So this was a very meaningful experience for me as well. The Challenges program, what you do is you have a program where the women are told every 2 weeks they need to submit an assignment. And then at the end of it, it adds up to a portfolio item. So I've got an illustration here for if you're applying to be a user experience designer, you would create a little design for an app, and that's what you would show as your portfolio. So of course, people could have done this on their own. They may not need a program. If we think about what are all the problems this is solving, well, we went out and interviewed the employers and asked the employers what they wanted and what would help them. And then this organization had some credibility. So we're convincing the women that it's worthwhile for them to complete the portfolio because this is going to be valued by the employers. And so it's really tailored to what employers want. So we kind of solved the chicken and egg problem by hand. It's a very cheap program, though. It costs about $15 a person. And that's just like administrative overhead, basically, like having somebody answer emails. In order to evaluate these 2 programs, we ran 2 parallel randomized controlled trials, randomized experiments. The challenges one was easier to describe. To have some truth in advertising, we accepted the first 100 applicants, and then after that, we said the program was reaching capacity, and we started randomizing them into treated and control. For the mentoring program, we had to deal with the fact that in the existing program, the mentors chose the mentees, and they felt that that was very important. They liked choosing their mentee, and these are volunteer mentors, so you don't want to take that away from them. So the way we finagled that is we asked the mentors to each choose 2 mentees, and then we randomized between them which one actually got mentored. And that way we controlled for selection. It also gives us this really nice opportunity to understand the role of selection, because we can see what's the difference between the people the mentors chose but who didn't get mentored and the regular population. And so all of that can be summarized on this graph with the 4 colored lines. We're showing over time since the program, the challenges control, the challenges treated, the mentoring control, and the mentoring treated. And you see the mentoring control group is way above even the challenges treatment group. And that's saying the mentors are really good at picking people who are likely to get a job anyway. And that, of course, but they still have a treatment effect. The light green boosts that even further. And I guess, again, if there are graduate students here, you might recognize some of that in your life, like the star students get the best advisors, but probably the best advisor still makes them better. But it's possible that social welfare would go up depending on how you weight the objective function if the best advisor actually mentored some more people in the middle too, because they might have even greater value added for those people. And so that's what I'm not going to be able to show you all of that, but we actually show that the people the mentors pick are not the ones with the highest treatment effects. But overall, the magnitude of the treatment effects is similar between the two in terms of getting a job, and although proportionally the effect is much larger for challenges because they're starting at a lower baseline. We then also look at some subgroups here, and we find, for example, that the challenges program has a bigger treatment effect for people with low experience. The mentoring works very well for people from small towns. And we interpret that as saying, well, people from small towns may be really well suited for a job in tech, but they just need somebody to help them introduce them to some people. So the mentoring might be really good for that, while the challenges program might be better for people who need to actually develop skills or who are less obviously suited and they need more than just an introduction. Okay, so that was the first project. The second project is about Coursera. And in this project, we're trying to understand whether getting a credential is going to help you get a job. And I'm going to say this again, but I just want to say it at the beginning. We are not studying the effect of having the credential. We are going to study the effect of the employers being aware of the credential. Okay? So we're just going to isolate the effect of making the employers be able to see it and verify it more easily. And that goes back to my earlier point. Once you've established that, then it's much more expensive to study the effect of having the credential, because then I have to get people to spend a lot of time. So EdTech is growing. Online platforms are growing. So I already covered that. So here we're going to look at these 2 research questions about showing the value of credentials. What we do in this case, we also build a new digital product together with Coursera engineers. And this new digital product is a product that makes it basically 2 clicks to have your credentials shown on your LinkedIn page. Okay, so it's an engineering feature inside of Coursera that connects to LinkedIn's API to get a verified credential. And then when you if an employer clicks on the credential, they'll come back to Coursera and see that it's a Coursera verified credential. Okay, so that's how the credentialing part works. And then we also have some nudges to try to get people to do those 2 clicks. So that's the overall policy. The policy is a 2-step process for showing your credentials and nudges that help you get there. So from a policy perspective, from Coursera's perspective, They just want to understand, is this a good thing, and should I release it to everybody? And based on the results of our work, they did release it to everybody. So that was good. So now, millions of people experiencing the feature. From an economics perspective, or more kind of structural perspective, we don't just want to know, did this particular implementation at this time with the nudges and the process work? We might also be interested in because, for example, people might not have complied with that nudge, and we see who they are. So we might instead be interested in the local average treatment effect, or the effect of the treatment on the people who were actually induced to post their credentials as a result of the treatment. And that's going to have more of a deeper economic interpretation. So we study both of these things, and I just want to highlight that it's not like one is right and one is wrong. They're answering different questions. The intent to treat is, what's the overall effect on everybody who is exposed? The local average treatment effect is, what's the effect on the people who were induced? So, so as we go through this process, then what happens is a Coursera learner completes a course, they receive their certificate, and only then do we do the randomization. So everybody in our sample has had the same experience up until after they receive their certificate. Okay? So the treatment group and control group both have certificates. Then we randomize them into the 2-click process where they get these nudges. We've got little examples of the boxes there. And then they choose to add it to their LinkedIn profile. Then we just watch their LinkedIn profile over time to see whether they get a new job. And so that solves a bunch of problems, because we're able to then to follow them for a long period of time, and we don't have to worry about non-response in asking them. The other way to do this would be to do it in a country and match it to data from governments. Very hard to do. Survey non-response just makes this super hard to do with just surveys. Most of the courses are audited for free. This is usually $29 to $99 courses, about $39 to $79 a month for a series on specializations and professional certificates. The sample that we use is restricted to those who are in developing countries or don't have bachelor's degrees. And that's partly we want to see the impact on people who are sort of more disadvantaged. Now we have 765,000 learners in the full sample, but only 37,000 of them have we matched to LinkedIn. And that's because we're using the LinkedIn links that they put in before randomization. And so we didn't intervene at the stage of getting them to share their LinkedIn profile. So that's a small subset, and in the paper we do a lot to kind of study who those people are. In the interest of time, let me just show you what kind of the results look like. We have the treatment and control group, and then the green is the control, the red is the treatment. I've got the dotted line showing because after the 7th month, we don't observe all of the cohorts anymore, so the sample is kind of changing as we go further out. But we see that there are treatment effects on getting a job. We then kind of break this out into a couple of categories. We look at what are the effects on getting a new job overall. That's kind of what I just showed you. And it's about 6 percentage points over the baseline. If we look at just people who get new jobs in the scope of what their credentials were, it's a lower baseline, actually a higher magnitude and a higher percentage. And then if we go to people who are getting a new job in the scope of their credential who didn't have an old job in scope, the sample shrinks even farther, and we get an even bigger percentage of baseline increase in treatment effects. So this is basic evidence that making it easy for people to show the credential to their employer is helpful. Then we look at the local average treatment effect, and essentially now we're adjusting for the fact that that a lot of people didn't comply. So in the first stage, only 3% are actually there's only a 3 percentage point increase on sharing the credential as a result of the treatment. So that then leads to a much larger second stage. The local average treatment effect is much larger because we're dividing by the low first stage. Actually, I think these results they're big standard errors. They're actually a little bit implausibly large. And so, there's some questions we're thinking about with that. For example, could it be that you actually bring it up in the interview because you were reminded about it? So there could be some violations of the exclusion restriction. And that might be a reason to focus on the intent to treat as well. We looked to see we did look at that to see if the feature got you more engaged in LinkedIn, and we didn't find any difference in the profile length or the activity on LinkedIn as a result of the treatment. We finally break this out. We use machine learning to divide people based on their pre-treatment characteristics into low employability, medium employability, and high employability. And we show that the magnitude, the absolute magnitude, as well as the percentage magnitude of the treatment effects are concentrated on the people who look like they had low employability at the beginning. And so that's hopefully showing that this is helpful. Okay, so now I'm actually going to switch gears a little bit. So first I said there's a problem, then I looked at 2 policy solutions. The last project I'm going to talk about doesn't fit quite as well. It's also about worker transitions, but it's about AI and it's about transformer models. And so everybody wants to talk about that now. So here I am. I actually started working on transformer models before ChatGPT came out, so I'm one of the cool kids. And I've got a series of papers. What I'm going to talk about today is a project about decomposing changes in gender wage gaps. I also want to mention that we've been, and that was based on custom transformer models, I'll show you. We've also got a couple of papers and more on the way where we're bringing in the large language models directly to economic modeling. Okay, so in labor economics, we want to understand transitions. I just showed you a bunch of reasons you might want to study transitions. We want good methods to predict the counterfactual. We want to know, what would you have done if you hadn't been subject to this intervention? There's another category of problems that I'll talk about today, which are called decompositions. And it's basically trying to say how much of, say, the gap between men and women's wages is accounted for by the fact the gap in today's wages is accounted for by the fact that you had different histories leading up till now, and how much is unexplained. And that can understanding the answer to that can help you with policies, because if everybody gets the same wages today, but just women had different histories, then you should intervene earlier in the career. Whereas if 2 people who have identical career histories have very different wages today, maybe you need to think about bargaining and other types of considerations. Okay, so we want to think about how to estimate and predict career transitions on small data sets. And that's challenging because actually if you think about saying what's the next job a person's going to have, if you have 10 years of career history, there's a lot of possible career histories you could have had. And so that's a very challenging problem. And so I'm going to, in this project, we're going to bring in modern AI methods to try to address that problem. So in particular, we're going to use the paradigm of foundation models and fine-tuning. So what is a foundation model? Well, everybody's used ChatGPT, so I'm not going to explain that to you. I'm going to talk a little bit about what makes it work. I say there's 3 big ideas. The first big idea of training one of these foundation models is that we need lots and lots of data, and they tend to be self-supervised. So if you have a paragraph, you're looking at that paragraph, and you're taking the first word and predicting the next word, first 2 words and predicting the third word, first 3 words and predicting the 4th word. That's the architecture behind ChatGPT and the architecture behind transformer models. But the key is I don't have to label what the words are. I just need a paragraph, and every word is the right answer to the problem of what comes next for the sentence before. So even one paragraph has a whole bunch of prediction problems, and if you have a whole bunch of paragraphs, then you have a lot of data. The second big idea is to use embedding functions, and that's basically to transform high-dimensional data into low-dimensional vectors. Those vectors don't have any direct meaning, but you can think about them as covariates that you might use in a regression. And so if you think about the space of all sentences in the world, there are many, many, many of them, but I'm going to reduce that to be captured in a 4,000-dimensional vector. And the key thing about these low-dimensional embeddings is that if you have 2 4,000-dimensional vectors that are close in Euclidean space, they're going to be close in meaning. And in particular, they'll be close in meaning to the extent that they can be used, they predict the same next word. Okay? That's the second key idea. The third idea, and you don't hear about this as much, but it's very, very common in industry right now and in parts of academia, is fine-tuning. And so that is, we start with, say, the model that Facebook put out, Llama, or another open source model, and then we take it to a smaller data set, and we continue the training just as if we were Meta training the big model, but we train it on our small data. So it's trying to predict the next word in a specific corpus of data, and then it gets much better at that. Okay? So those are the three big ideas of the foundation models, and we're going to make use of those in career trajectory predictions. So in particular, if we suppose our end goal was now to predict wages. So we want to take the history of jobs and use that to predict wages. Well, if we wanted to be fully non-parametric, we could delineate all the possible histories, which is a very large number, and have an indicator for whether you had that particular history. But there's too many histories, like more than probably atoms in the universe. So too many histories, so we need to reduce the dimensionality. So then how do we do that? Well, it's going to be hard to reduce the dimensionality in a government survey data set. Say I have the PSID or the NLS at Y, I have tens of thousands of people, maybe 100,000 transitions. That's not enough to learn a great representation of what jobs mean and what sequences of jobs are common. So what we want to do is bring in some other foundational information. So in particular, what do we do in this project is we get a data set of 23 million resumes, so that's a lot of resumes, and then we build a custom transformer model to try to predict the next job in a sequence. So just like, and this is just like what the text models do, they predict the next word, but jobs are words. So the architecture works just as well. There might be 30,000 words or 50,000 tokens that you use, and there's 330 jobs, so it's a smaller problem. That's why I could do it on Stanford machines and not using $100 million to do it. But it's the same exact model, except we're gonna improve on it in a couple of ways for this application. So what we start with is just the next job prediction problem, no wages, because I don't have any wages in my 23 million resumes. I just have next jobs. So you think, how is that going to help me with wages? Well, it doesn't help me with wages directly, but it helps me indirectly, because it helps me understand the meanings of jobs, and it helps me understand the meanings of job sequences. And if I can understand job sequences well enough to predict your next job, then I probably also understand something that's relevant for wages. So that's the idea. So we basically train a representation to predict the transitions. And this lambda theta of H, that's a function that maps from the job history into, in our case, it's I think 980 dimensional vector. And that's the representation we use. So putting these pieces together, the pre-training or the foundation model training is done with resumes. The input is just sequences of jobs. And our goal is to predict the next job. And then we learn a representation. Then we move to survey data set where we do have wages. It's smaller. And we just keep training, but now we don't train to predict the next job. We train to predict wage. Okay? So that's our model. We do a few other things. We allow covariates, and we also give special treatment to staying in the same job, because you don't say bird, 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 but you do stay, waiter, 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 waiter. So we modify the architecture a little bit. So just formally fine-tuning, there's these parameters theta of the embedding function, lambda theta, it's a neural network. We take gradients of the objective function, and we train the parameters theta in the resumes. Then we stop, and we load up the survey data, and then we keep training those same parameters theta, but with a different objective function and different gradients and different data. And we minimize mean squared error. And at the end of that, we have parameters theta with parameterize this function lambda theta that maps from histories to a 1,000-dimensional vector. And then we can treat those as if they're data and use them as we like. So if we compare that to what we typically did in economics, and I like this problem of the gender wage gap because there's actually like tens of thousands of papers that have studied this, and there's like hundreds of thousands of papers on wage regressions. So it's got to give a fair fight to machine learning, because if you think about all the research assistants and all the regressions they've run, it's a lot of regressions that have been wage regressions that have been run. But the restriction is often just that, there's so many combinations of covariates, and you run out of data. So these embeddings kind of reduce the dimensionality and start with some structure so that we can incorporate richer history. So we compare our model to a model with just 21 categories, coarse-grained occupations. That's something that's commonly used. You can also use 330 occupations. It already starts pushing the limits of the data. And then we also try lasso, although that's not commonly done. And we include constructed summary statistics of the data, like region, union status instead. Our alternative is that we include a shallow neural network, a simple function of our 1,000-dimensional embedding in the model. And then we look at held out R² in a test set. So if we look at the standard labor economics models, the R² is about 0.42. Jumping to the bold, our model gets you to about 0.52. So despite all those research assistants and all those years of regression running, we got a 25% improvement in the R². And the improvement is not only due to functional form of the current occupation or capturing workforce participation spells, it's really using the full history. So then we go to gender wage decompositions. And when you do a gender wage decomposition, actually you care not just about predicting wage, but actually about predicting differences in wages between men and women. Estimating, it's not the same as estimating treatment effects conceptually, but statistically it's the same as estimating treatment effects conditioning on covariates. And so what decompositions do is they say, I'm going to take the part of the gender wage gap that is explained by the fact that men and women have different histories at a point in time. Take that one part, then there's another part which says if they had the same histories, what's the difference in the wages? So we prove a new theorem, which I'm running out of time, so I'm not going to be able to talk to you very much about, but let me just say verbally what the contribution of the theorem is. We have a whole theory about how to estimate treatment effects under unconfoundedness and how to do decompositions when there's a small number of x's. We show that you can apply the same theorems as if these estimated embeddings are actual data, and the same theorems applied, only conditioning on the embedding, as long as we get rid of omitted variable files fast enough. And then we come up with methods that target omitted variable bias. And the basic idea is the only thing that's going to screw up a gender wage gap are variables that are correlated with wage and correlated with gender. And so in our optimization routine, we optimize for finding those variables. And it turns out the magic method is the same as for my heterogeneous treatment effect work that we use in our GRF package. So we find that when we start optimizing for not having omitted variable bias, it could make prediction worse, it could make it better. It turns out it makes it just a tiny bit better in our case, which is kind of interesting in and of itself, because it's saying that actually you're not harmed by trying to do this extra thing. By thinking about both gender and wage at the same time, it actually helps you a little bit. And then this last slide, I just want to give you some interpretation of what we find. It's actually very hard to interpret these models, and so we came up with kind of a heuristic approach. We built kind of a regression tree that tried to predict what are the most important categories or groupings of these embeddings in terms of predicting wages, conditional on the current job. So manager is a really big current job, and then we find the ones that have the biggest improvement in R². And so here, what I'm showing you are the subdivisions, the top 5 subdivisions of manager based on our embeddings that predict wages the most. We've got software developer, and then the words are the jobs in the history, not the current job, but the jobs in the history. So if you're a manager today, but you were an electrical engineer yesterday, that's very predictive of your wage. It's also very predictive of your gender. And so it's 11% female in our sample. This is a big contributor to the unadjusted gender wage gap. Similarly, if your past job included cashier and homemaker, that's a job that's and now you're a manager. You're 93% female, and the wages are low. Okay, so now you start to see how adjusting for more and more of history can start untangling and disambiguating what some of these jobs are. But there's other jobs too. Even sales jobs have a wide range, and you get clues about what kind of a sales job it is from their previous history. And if nobody had ever run one of these regressions before, you could just say, no duh, Susan, your machine learning program figured out the obvious. But there's hundreds of thousands of regressions have been run, and people ran out of data, and they didn't include all these things. And so that's partly what's going on. Okay, so that's the last slide, and this slide is actually showing we try a couple of different ways to do this, and actually all of the different methods. This is kind of just technical to do the debiasing of these models, and we find that all of them explain about 17% of the remaining wage gap when history is not included. So it's not a huge change, but it's a change. So overall, I think this shows that these transformer models have a lot of promise, and they allow us to study dynamics in ways that we maybe thought was hopeless. This is just the beginning of how to do this, but I expect that we're going to see a lot more action in economics, because it's not like people didn't want to do this, it's just that we thought we couldn't do it with the data that we had. It turns out that using foundation models gives you a big boost up to then study problems in smaller data sets. Thank you.